Hi, my name is Dr Alikhani. I am Dean and Professor at CTOR Academy, and I'd like to welcome you to another session of CTOR channel. Today, we are planning to talk about material as a source of our forces. After we design our mechanotherapy, it is time to select the material that we are going to use to provide the forces that we have designed for our mechanotherapy. In general, in orthodontics, we are using three types of materials: metals, such as wires and springs; elastomers, such as power chains or rubber bands; and biological materials. For example, we are stretching the lip, and the lip wants to go back to original shape, and similar to any non-biological material, produces a forces. In all these conditions, by application of a force to the material, we deflect the material wants to go back to original position, produce a force that we gradually release it to our biological target to move the biological target. In all these conditions, we are hoping that we do not apply too much load to our materials that material breaks. If the material breaks, cannot be the source of our force. Therefore, understanding the property of our material and what is the best way to use them as a source of the force is necessary. In this session and future session, the word load and force have the same meaning. When we are applying a force on the material, we call it loading or activation. When we are allowing the material to release the force, we call it unloading or deactivation. To select the best material for our mechanotherapy design, we need to know the property of the material. Let's start with some material that we are all familiar. The most common one is the wire. If we applied a force on the wire, we are expecting that the wire to produce a force in opposite direction. But how we can load or apply a force on the wire? We can apply a force or load along the long axis of the wire. We call it, for example, by stretching tensile loads, or by pressing compressive load. Or we can apply a load perpendicular to the long axis of the wire that we can call it shear load or shear force. In orthodontics, we usually do not apply a load along the long axis of the wire, but mostly we apply a force along perpendicular to the long axis of the wire, such as shear loads, as a source of our force. What happened to the wire when we apply a force perpendicular to its long axis? Let's look at that. We're connecting the wire to the wall from one side, and we're applying a perpendicular force in the other side. What happens if we apply a low magnitude of the force? You will see the wire deflects, and if we remove our force, the wire goes back to original position. What happens if I increase the magnitude of the force? The wire deflects more, and if I remove the force, the wire goes back to original position. If I continue this exercise, I reach to the point when I'm increasing my magnitude of the force and I remove my force, the wire does not go back to original position and accept some permanent deformation. If I continue to increase my force even more, you see that this permanent deformation increase more to the level that if I remove my force, the amount of the recovery of the wire is very minimal. At this stage, that wire does not have clinical usage anymore. Most of the time in clinic, we apply a load to the wire at the level that it can go back to original position or demonstrate a small amount of permanent deformation. But why wire demonstrate this property? That's because between the atoms of the metal, there is a bond. As long as we are stretching these bonds because of our forces, this force stays in those bonds as potential energy. When you remove the source of the force, this potential energy releases itself, goes back to original position, and produces a force for us. If we bypass this stretch between the atoms to this certain level that the atomic plane slide on top of each other, then at that time permanent deformation appears. and you continue this, you can reach the failure point. Means that now the bonds are cut. If we go back to the example that we connected the wire to the wall and we are deflecting the wire to the level that it can go back to original position after removal of the force, that is called range. The amount of the deflection that wire can accept before demonstrating any permanent deformation. On the other hand, if we deflect the wire even more and the wire cannot completely go back to its original position, that is called a spring back. Means we bypass the range and now we demonstrating some permanent deformation. Let's put all this information in a graph. This graph is called load deflection graph. How much load I applied, how much deflection I get. As you can expect, at the start of this graph, there is no deflection inside the wire. So the line of the loading of the wire across the both axes at 0 point. Now, if you're increasing your load, the deflection goes up, goes up, goes up until you're reaching a place that after that, the material does not go back to original position. That point is elastic limit of that material. After that, the permanent deformation appears. If I increase my force, the permanent deformation increases. So as we discussed before, the clinical application of the wire is at this elastic limit or early stage of this plastic limit. If permanent deformation increases significantly, the wire does not go back to its original position and therefore clinical usage of it decreases significantly. We reach a point, we call it ultimate strength, that after that is actually wire not only does not go back to original position, does not release a force that we expecting to release. That's the ultimate strength of the wire. After ultimate strength of the wire, by continuing application of the load on the wire, we just push the wire toward the failure point. Load deflection graph is the base for understanding the stress strain graph that would be the subject of the next discussion. I hope you enjoyed this session of CTOR channel. If you have not subscribed to our channel, please go ahead and subscribe, and please don't forget to press the like button. Thank you.